So good afternoon, everybody. I'm Tyler. I'm going to talk to you about data engineering with Rust. I don't expect everybody here to know Rust. Emily, would you mind if you pulled me down a little bit? I'm just getting some echo on my side. Thank you. I'm not expecting everybody to know Rust, to be super elite Rust hacksaws for this talk. I'm not going to be talking about anything that is necessarily heavy, deep in the internals of Rust for this discussion. But I would strongly encourage that if you're interested in Rust, if you're only just getting started, the Rust book, as it is called, is a really good read. I would encourage you to do that along with, shoot, what's that thing called? There's a Rustation's little, Rustlings, that's what it is. Rustlings is also a really good way to get started in learning Rust. For my own Rust journey, I started learning Rust probably 4 or 5 years ago, and then I started learning Rust again 3 to 4 years ago, and the second time or third time around, it actually stuck. I have the fortune or misfortune of being one of the maintainers of the Delta Lake Rust package. A couple other folks who also work on the Delta Lake Rust package are here. My colleague QP, or I guess my ex-colleague QP, and I created it at Scribd in 2020, I think. Late 2020, and it's now grown into this very, I would say, widely used Delta Lake implementation in Python and Rust. But the reason that we started with Rust was a fundamental belief that QP and I had at the time that A, Rust was really cool, we liked it, and that chutzpah that you have when you step into a project just because you like the technology does help you get over some of those initial hurdles. But we also very much believe that the zero runtime that Rust has would allow it to be embedded and extended in a way that the Delta Lake Rust project actually has over the last few years. So we didn't start with a Python binding, but a Python binding grew quickly out of the Delta Lake Rust ecosystem because Rust lent itself to being so embeddable and such a high performance language for us to work with. Some of the other things that I've been doing since my team at Scribd, we wrote Kafka Delta Ingest, which is another open source project. We'll talk a little bit about that in this talk. But that's the reason, the motivating factor originally behind Delta for Rust. I authored a book, or a chapter in the book that's going to be coming out, the Delta Lake Definitive Guide, that will talk more about some of the concepts with data fusion and other things that we'll talk about today as well. Generally speaking, I like to write Rust for all of the things because Rust is super cool, and if you write Rust, you'll be super cool too. Anyways, so I want to define a couple terms just to make sure that we're all on the same page. First is Delta Lake. If you're not already familiar with Delta Lake, you're about to be. Delta Lake is a very simple, conceptually, protocol in that it's JSON-based log files and conventionally Apache Parquet formatted data files sitting on the file system in an object store kind of anywhere. And in my totally pretend but very realistic Delta table that we see on the screen, we've got 2 partitions. So this is Hive-style partitioning. There's a DS partition with the data for April 1st, and then a Hive-style partition for the data on April 2nd. And then there's a Delta log directory, which has 1 JSON file, 00 blah, 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 .json. So that's the first transaction, 000.json. That's the first transaction in this Delta table. And if we look at that 000.json, you'll actually see what Delta Lake is under the covers. And so this is typically what you will see in almost every Delta table. When you first open up the first transaction, you'll see the commit info, which is optional according to the protocol, but it is not optional according to most readers and implementations that exist out there, and they will complain if it doesn't exist. You don't have to worry about that. The library underneath has to worry about it. We've got a protocol action. So this is JSON lines, a protocol action, which defines who can read and write this. Other data may be in those Delta, that protocol action for newer tables. We have a metadata action, which actually defines our schema, gnarly as it may look on this screen. It's a JSON serialized string under schema string here at the right-hand side. And then we have a couple of add actions. Add and remove actions are where the rubber meets the road with Delta Lake. In this case, all 4 of those Parquet data files have been added in this initial transaction. So if a reader comes along and it loads this Delta table, it's going to see these 4 files have my data, and that there's a partition column of C2. And in some cases, we have file statistics that may be added on those add actions that help the reader, Spark, pandas, whatever, pick the right data files to load. So that's, in a nutshell, what Delta Lake is. Very useful to know. And part of the reason why I wanted to start by explaining a little bit about how Delta works under the covers is one of the really useful things about the Delta RS library and building things in Rust is there is a pretty straightforward path between you as an implementer of a system and the Delta transaction log in the Rust bindings that allow you to do interesting things and derive interesting insights that you might not otherwise get from a like describe detail or describe history Spark SQL command. And you can do it very, very quickly and easily because you're going straight to that Delta transaction log. You're not invoking a JVM or anything like that. So hopefully everybody knows what Rust is. This is what Wikipedia says Rust is. The big reason that I think Rust is interesting in the data engineering space is because there's no overhead, and that means there's no garbage collector. So the JVM has the garbage collector, which means in a lot of cases, as your system scales up, behavior will change depending on how much data is being recycled as time goes on. With Rust, it has no garbage collection. It's going to manage, you, in effect, are going to manage your objects directly in some form or fashion. And so the scale is much, or the throughput of a data system is much more predictable from a, let's say, a 1,000 messages per second to a 10,000 messages per second on the same program. It's going to largely look the same in how it performs. That's one of the things that makes Rust for data engineering so interesting to me, is that it predictably scales in a way that I have not seen JVM or other data systems scale. I mean, Rust is also just super cool. So when we're talking about data engineering in Rust, we're typically involving a couple of these tools. We're talking about Delta Lake here because I work on Delta Lake, and Delta Lake is super cool, and we all want to be super cool too. But underneath the Delta Lake library, there's a couple of interesting libraries that we depend on. One is the Arrow library. And the Arrow library is probably the most foundational crate that ever existed in all of data engineering with Rust. Arrow kind of underpins everything. And the reason Arrow underpins everything is because it's a high-performance, compact, in-memory engine. So representing our columnar data, like from an Apache Parquet file, is very trivial, very fast with Apache Arrow. Working with Apache Arrow is a little, how do I say it? This is actual Rust. This will compile, assuming that you've got the right imports. Arrow is not the most user-friendly library to work with. I recommend looking at Arrow from afar and saying, great, I'm going to use something else. One such library that is that something else that is really, I would say, idiomatic in the Rust ecosystem is this library called Serde Arrow. Everything in Arrow that we work with when we're talking about writing a data to a Parquet file or reading data from a Parquet file, doing a merge or doing anything interesting, our primitive is record batch. And so what we've got on the previous slide, we're creating a record batch the hard way. This sucks. Serde Arrow makes it very idiomatically sane to create record batches from just Rust objects and then do interesting things with those record batches. We're of course going to talk about the Delta Lake crate. Delta Lake crate, super cool, maintained by really cool guys and gals. But a couple of things that are interesting about the Delta Lake crate, if you go grab it right now, and you all should because it's available today, it's actually a couple of different crates. So there's the sort of meta crate of Delta Lake, and if you just do a cargo add Delta Lake, you'll get a whole bunch of other things that are controlled by cargo features that'll give you different support for things like AWS or Azure or GCP. You can also pull these independently. We've structured the project to where if you have a very small daemon that just works on GCP and it only needs to touch these specific things, you can grab Delta Lake Core and Delta Lake GCP, and you can construct these things yourself and get a very slimmed down binary to do your really fancy GCP thing. For the purposes of this talk, just cargo add Delta Lake. In this case, we're adding the Data Fusion feature, which means I get to introduce Data Fusion. Similar to Arrow, almost everything in the data engineering with Rust space uses Data Fusion in some form or fashion. The reason for that is Data Fusion is A, really well done. Like, very big kudos to the team that's been working on data fusion over the last couple of years. It's matured quite well, and it gives us a couple of things. It gives us this data frame API, and if you've worked in Spark or Pandas or Polars or anything that has a thing that's called a data frame, that data frame API will feel very familiar to you. But it also gives us a SQL dialect. So it can run SQL for you, but it will run Data Fusion SQL. It will not run Spark SQL. It will not run Hive SQL. It will not run MySQL or PostgreSQL. Data Fusion SQL is its sort of own interesting SQL dialect, and so it's worth looking at, but bear in mind that it is a distinct SQL dialect unto Data Fusion itself. In the example earlier, the savvy audience member may have noticed await. Rust has async and await, and these are very useful and very important when we're building our data engineering systems because they give us concurrency in a sensible way. But for most people that come into Rust, they can be confusing because of how they work. When I call Delta Lake open table on my path, nothing happens. I get a future. Nothing happens until I await that future, and then I get a response. And this is something that will trip up a lot of people because they'll create things or they'll call functions that give them a future and they never await on them, and so they never get a result and they don't get their data, their record batch or what have you. And Data Fusion, Delta Lake, and I don't think Arrow, but most of Data Fusion and the Delta Lake library use async and await quite heavily. And so it's useful to always be mindful when you're looking at docs, and docs.rs is a really good bookmark to add, where you've got an async keyword on your functions, because those you will have to await before you get that data back. I do also want to mention references, just for the non-Rust initiated. There's a couple of different ways we can refer to things in Rust. Ownership is a big thing with Rust. If you don't own the data, that means you can't change the data. And so line number 1, we can't send that reference between threads safely. There are some caveats here. I don't need any hecklers from the Data Lake folks in the back on that one. But that basically means we can't send it between threads safely, and so the compiler will complain. So what most people do is they'll wrap that thing in an arc. That's an atomic reference count. So whenever you see arc in Rust code, and you'll see it a lot in the Data Fusion and the Arrow examples, arc is just a thing that can be shared between threads safely because somebody's doing a reference count, and when that reference count hits 0, then Rust will drop the memory. And then arc mutex, you don't see this as much in the Data Fusion or the Arrow code, but that's just something that can be shared between threads and modified because there's a lock wrapped around it. I just wanted to highlight that because we'll see some of these things come up in code shortly. Okay, so Nick, who's working on the Delta kernel in Rust, he's back there in orange. Nick will wave to everybody if you've got any questions about, everybody look at Nick. He was asking if this was a real terminal connected over the internet. This is a real terminal connected over the internet, and the reason it's connected over the internet in a real terminal is because this code's actually gonna run, so I'm tempting fate on 2 axes that my demos are gonna work correctly. So, we're gonna do some data engineering. Step 1, we need a Rust project. In most cases, you wanna create a Rust binary. A Rust binary you can shove into a Docker container. You can shove it into, you honestly can shove it into Airflow directly and just have it run on your Airflow workers if you wanted to. I'm not recommending that. But generally speaking, we wanna build a binary. And our binary is gonna go grab our data and do whatever we're gonna do. And then we wanna compile it. In this case, cargo run is running some code that I've actually sort of snuck behind the scenes. But we're reading a Delta table, and so let's look at that code. So when you start your Rust project, 2 dependencies that you'll definitely need to do some really cool data engineering. One is Tokyo, and remember async await. Async await doesn't do anything in the Rust ecosystem unless you have something like Tokyo, async standard, or something else that will run your futures. And we need Tokyo to run our futures. So when we say my Delta table is going to open and I'm gonna await on it, something has to actually be running the thing. This is not a runtime in the traditional sense. It's really kind of like a reactor pattern. So if you've ever worked in, I might be dating myself here, like Twisted Python or Stackless or things that have reactors, Tokyo is basically a reactor pattern for those async awaits. So we need Tokyo, and then we need the Delta Lake library, and we're gonna add the Data Fusion feature because Data Fusion is going to add lots of really interesting things for us. And so when you do cargo add is going to add those dependencies to your cargo toml. That's your requirements.txt in Rust or your pom.xml, I guess. Typically, your Rust project is going to contain a lot more dependencies because you're going to do a lot more interesting things than this contrived example. But what's really useful is just with these two dependencies, will pull in a lot of the other foundational things that you will need to work with a Delta table and to do something interesting. So by pulling in the Data Fusion library, we can do all those interesting data frame things, and it pulls in Arrow underneath, and we can read from Azure, and we can read from S3, just through these two dependencies at the top level. Okay, now we're gonna get into some meaty Rust code. All of my examples are gonna be using Data Fusion. I wanna make the caveat here that you can do a lot of data engineering, interesting things without Data Fusion, but you will be choosing the path that's less often taken. Kafka Delta Ingest, which I mentioned earlier, does not use Data Fusion. Kafka Delta Ingest appends data at a very, very high rate of speed from Kafka into Delta tables. It's an open source project. You can go look at it. You can look at all the Rust code that exists for that. Doesn't use Data Fusion, but for beginners, if you're just getting started, Data Fusion has all of the batteries included. It's probably gonna feel the most familiar to you, so I would recommend starting with it until you can find ways to optimize it out, assuming that you need to optimize it out. So in this example, we're gonna create a new Data Fusion session context. This is similar to your Spark session, if you're coming from Spark. And the Delta Lake library adds a lot of data. It adds what's called a table provider behind the scenes when you register a table. And so we'll be able to query that Delta table. So we're gonna register the table. I actually have line highlighting. What am I doing? We can go here. When we register the table in that context, it's similar to adding tables in your Spark context. There's a lot of similarities in how these APIs work between Data Fusion and Spark. So syntax aside, you should be able to logically map some of the concepts from one to the other. And then on that session context, I'm going to execute some SQL. This is Data Fusion SQL, as I mentioned before. A couple of things that I should note about this. Context.sql is going to give us a future that we have to await upon. And there's this question mark, which when I first started learning Rust confused the hell out of me, because why is there a question mark there? I know what I'm doing. Question mark is going to unwrap a result or an option in some cases, and will bubble it up. So it's a way of bubbling up this error, if an error is to exist, to the caller without needing to add additional syntax sugar. So when you're looking at Rust examples online, you may see that. You may see people do like await.unwrap, .unwrap, or .expect or whatever, and they're just unwrapping a result type and then passing it up. But in this case, we're using the shorthand, so the caller is gonna have to know how to handle a Data Fusion error. And then collect is actually resolving that data frame, because context SQL in Data Fusion actually just gives you a data frame. And once you have a data frame, you can do really interesting things with it. I should have hit Control E when I first started talking, because now it's got to actually compile and run this. But in this case, what we're gonna get after we collect and await is we're gonna get batches. So as I mentioned before, record batch is the primitive, like that's the key data type below everything. And once we have batches, we can use Arrow to print the batches. The captioning, I didn't realize was gonna cut into that, but there's 3 rows there, and they're incredible. It's a really great and useful Delta table. But just with this, we already have something that's very, very powerful, because we're opening a Delta table. That's step 1 for a successful project of any kind. But we're creating a data frame. That's gonna be probably the most useful thing to really get comfortable with, is turning a Delta table into data frames, because once you have a data frame, there's so many operations that you're familiar with from Spark that you can just start using directly from Rust. As I mentioned, data frames are very important. The nice thing about data frames is once we create a data frame with Data Fusion, we're sort of outside of the realm of Delta Lake. We've gotten the data that we need from Delta Lake in sorts, and we can go into the rest of Data Fusion and do interesting things with that data. But that also means that we can pull data frames from other sources. In this case, from a CSV file, we can get a data frame and do something useful with that. And in this case, I want to take my example CSV. I'm going to get a data frame out of that. And then I'm going to use Delta Ops. In the Delta Lake library, most of the cool stuff that you want to do with a Delta table is under this Delta Ops module. We follow a builder pattern. And so I'm going to create a Delta Ops write builder from my table. And I'm just going to pass it some record batches, because record batches is how we do all of our work. And what this is actually going to do underneath the covers is we're going to write another transaction. It's going to write a data file based on my example CSV. So I'm starting with CSV input. I'm going to create Parquet output. And then I'm going to write that to the Delta table. So here's my super cool CSV with two other super cool. 707 is the area code in Santa Rosa. SR City is, I mean, it doesn't matter. Anyways. So this is the table that we're starting from. This is what we're going to write to. As we looked at before, we've got a couple of partitions. The columns have changed just because it's not contrived. It's a real table this time. And I'm going to run this code. And all I'm doing is I'm just copying the data. And I'm using the same write main that you just saw with the session context, the blah, 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 blah. And it's running. One of the reasons I highlight the challenge with Data Fusion is Data Fusion's a big library. And so you see that took a little while. This machine's not the fastest. It's not the slowest either. But Data Fusion does add a lot of link time dependencies, which for most projects are totally worth it. But it does change, like if you're used to instant response times from your development, coming from JavaScript or Ruby or Python, working with Rust can be a little bit slower in that regard because you're going through this compile run cycle. But anyways, we've run through the code and we've appended this 707 SR City row to the table. And so let's look at the table. Look at that beautiful table. So we now have another Parquet file. We've read a CSV file in, and we've created a new Parquet file with new data and another transaction. And that transaction, I'm not going to show you that, but that transaction file just contains another add action that we had before to add this sucker. Just looking at my time. So I'm not going to be going through every operation that exists in the Delta Ops module. If you go to docs.rs and search for Delta Lake, you'll be able to pull this documentation up. But from Delta Ops, in that same pattern as before, and let me jump back real quick just to show you the pattern. Whoop, too far. With the same pattern, if you replace write with merge, merge takes different arguments. You can start to do merges. If you change it to update, you can do an update builder, and you can start updating rows in tables and things like that. There's also compact, vacuum, Z-order. I don't remember all the ones. But this Delta Ops module is very, very powerful and has a lot of these operations that you can do. And as long as you're pulling data into a Data Fusion data frame, you can kind of do almost anything that you would be doing in Spark, or almost anything that you're doing in Pandas or Polars straight from Data Fusion with the Delta Lake library. All of these options, or all of these operations, not options, are compiled to be enabled with that Data Fusion flag. So we did cargo add features Data Fusion. If you omit Data Fusion, if you build your project with the Delta Lake crate without Data Fusion, some of these operations are not available. Because for things like merge or update, we have to resolve table state at the beginning of the process. I normally use both hands, but I hurt myself, so. At the left side of the process, we have to read from the table. We have to then create the update transaction. And so many of these do require Data Fusion to do that. If you're just writing or appending to a Delta table, or just looking to do transaction log management, you can pull in the Delta Lake crate without Data Fusion. I've been blitzing through this, I'm sorry. Data Fusion is just so exciting. So I mentioned a non-Data Fusion example of Kafka Delta Ingest. Kafka Delta Ingest, super cool project, ingests data from Kafka if you've got high volumes of Avro or JSON data coming into Kafka, it can take that from one topic, goes from there, boom, into your Delta table. Brilliant, cheap, way cheaper than running a Spark cluster to do the same. But it does some interesting things with the Delta table that you can also do if you are working with the Delta table in Rust. I've got a snippet from the protocol here, this JSON here. Similar to that transaction that we looked at before, that transaction file, we've got a commit info, contents irrelevant, some add transactions, contents irrelevant, and what my colleague Christian Williams and I named the Texan transaction. So the Texan is user-defined for the commit on the Delta table. And the whole reason that action exists is so that you can keep track of streaming state. It was originally designed for Spark streaming workloads, but Kafka Delta ingest actually uses this to keep track of consuming from Kafka topics, so the offset of a particular topic. It keeps track of that in the Delta log as it consumes from Kafka. And so Kafka Delta ingest, when you deploy it, you are able to stream data very, very quickly from Kafka, comes into the daemon, spits out into Parquet files, and transactions land in the Delta table. And the only state, the only runtime state that it holds is actually in the Delta table itself, using the Texan action, which is an incredibly powerful thing if you think about using Rust and Delta tables as a sort of streaming application data source. One thing, I think Kafka Delta ingest is really a useful tool. It's not the best documented. That's kind of my fault as well. But one of the things that's sort of nuanced about it is Kafka doesn't guarantee ordering on the topic. It guarantees ordering on the topic partition. And so typically with Kafka Delta ingest, because we're running this daemon sort of to consume, but there's no coordinator. When you're consuming from a Kafka topic in Spark, you've got your driver that will coordinate consumption to your workers that are then going to be writing out to the Delta table. With Kafka Delta ingest, that does not exist. And so you have to sort of be thoughtful about deploying this so that you can deploy it. In this case, we typically deploy one instance of this daemon per topic partition tuple pair, so that each topic partition is being consumed from and written to the Delta table in order. And so with Rust, you can do really interesting things with Delta tables. You can do even more interesting things once you know about this one simple trick, the Texan action, which lets you keep track of state inside of the Delta table without needing to modify the Parquet data files as you move along in consuming data. And if you think about, not necessarily Kafka, but any sort of streaming system, or even just I'm ingesting from X location and I've got some offset, I can store that through the Texan action in the Delta transaction log. It works out really well. If you want to see Rust code that was written by people who are just getting familiar with Rust, Kafka Delta ingest is a great code base to look at. We've made mistakes there. If you want to see Rust code that's written by some people who really know what the hell they're doing, check out Arroyo. So arroyo.dev is a really interesting project. It was open sourced by a couple of guys that came out of Y Combinator last year, I want to say. And the interesting thing about arroyo.dev is, or Arroyo, but arroyo.dev is where you can find them, is it is a stream processing engine fully written in Rust. It does work with Delta Lake, but it works with a lot of other things as well. But their underlying premise is that they wanted to expose SQL as the user interface for stream processing. If you've ever worked with Apache Storm, Spark Structured Streaming, Flink, like stream processing is kind of a difficult thing for most developers to wrap their minds around. Delta Live Tables and Arroyo sort of take this SQL-oriented approach. This is entirely built on Rust, obviously, and Data Fusion, and Arrow, and in this case, the Delta Lake library, and some other really cool tools that make data engineering, really shine, I think, in Rust. It's relatively lightweight as far as a system footprint goes because of that choice with Rust, but it's a really interesting project to look at. I shared this example just because I wanted to give them some props for building a really great Delta integration, but I also wanted to highlight Arroyo because Arroyo is a great example of where Rust shines in data engineering, where we're building data systems. So the interface of SQL, most data analysts, data scientists want to work with something like SQL or Pandas data frames, but when we're building ingestion systems, high throughput systems, things that are at a more foundational level of our data infrastructure, that's where I think Rust should go. I am not suggesting that anybody necessarily introduce data scientists to Rust. I don't know how productive they would be versus just sticking with Python, where, I mean, Python is really good at that layer. But for data systems like Arroyo, it makes sense. Let's see. So there's a couple other interesting projects that I wanted to highlight for y'all to look at as well. These are all written in Rust in varying flavors. Row API is just GitHub/RO API. That was created by QP, who also created Delta RS. And the interesting thing about Row API is, A, it's in Rust, but it is similar to Arroyo in that it's like connect anything to anything sort of thing. It will present a read-only API of Delta tables, CSV files, S3 buckets, all sorts of things. And it's also another, I'd say, it's a relatively constrained code base to look and get familiar with how some of these data problems can be solved in Rust. ParadeDB recently introduced a Delta Lake integration, and what ParadeDB is doing is they're pulling, they've got a Postgres extension called PG_Lakehouse, and so if you want to query a Delta table from within Postgres, which is like mind-blown sort of cosmic brain type stuff, PG Lakehouse does that, and the reason that they chose Rust is so that they can embed whatever they're doing inside of Postgres. So Postgres, I believe, is a C or C++ project, but it has that sort of CFFI extension boundary that you can build a Postgres extension with in Rust. So you can work in a type-safe language like Rust, and they pull Delta Lake and a lot of other interesting things directly into Postgres because it's written in Rust. The final thing that I wanted to highlight here is a relatively recent project called Apache Comet. Andy Grove, who created Data Fusion originally, started a project called Ballista, and I think Ballista is kind of petering out. But Ballista was trying to build Spark in Rust. Spark is incredible, it does lots of things really well, but there's no equivalent in Rust. So Ballista was trying to solve that problem, and then a group of folks came along and said, hey, we've been working on this Skunkworks project, what if we want to open source it? And it turns out that became Apache Comet, which is trying to solve sort of that same fundamental thing of like, I want to build a Spark, but in Rust, because there's a lot of benefits that we get from building it in Rust. And so Apache Comet is also something interesting to go look at. I don't believe they support Delta Lake through the Delta RS crate yet, but I'm not sure. Okay, so first of all, I made this mistake earlier. Earlier, I asked for questions, and then I said thanks, and a bunch of people left because they didn't have any questions. So I'm going to say thanks so I can get the applause now, but then I will answer any questions. Thank you.